Welcome to the presentation of the ACMCHI 2024 paper Loopsense. We present novel small-scale knitted sensor cells that are made of single pairs of loops and are easy to conceal in a variety of knit structures. We are furthermore able to discern between actuation modalities of vertical strain and horizontal strain, as well as pressure. We achieve this by selectively modifying stitch types of the sensor cells to create loop mesh variations that result in specific sensor characteristics. My name is Roland Aigner, and this research has been conducted together with my colleague Mira Haberfellner and with Professor Michael Haller. Knitted user interfaces have a long history in HCI research, where sensing methods are typically based on measurements of capacitance, impedance, or electrical resistance. For each of them, there are ideal application scenarios, as well as certain strengths and downsides, which is also the case for the method we use in this paper, which is the resistive method. An advantage of this method is that resistive sensors are rather easy to calibrate and operate. However, a more fundamental motivation for using resistive sensing in our work is more related to the physical nature of knits. A property of this type of fabric is that it is inherently stretchable. This is due to the loop structure, which gives the yarn slack and allows for geometric rearrangement. This contrasts to a weave, for example, where the yarn is traveling straight, and the structure inhibits stretching, unless of course the yarn itself is elastic. So this property of a knit makes it an ideal and frequent candidate for sensing not only surface pressure, but also strain. And for this reason, we use resistive sensing, which is basically measuring the effect of force on a certain material. But to be precise, we are talking not only about one, but a combination of materials. This work of Weiss and Warren describes the working principle of a well-known electrical element, a force-sensitive resistor or FSR, where metal electrodes are in contact with a resistive film that is usually made of a conductive polymer. At rest, the surfaces are in little contact, but if compressed, the contact area rises and therefore the electrical resistance drops, which can be measured quite easily. All you need is an Arduino board and a voltage divider. For knitted sensors, this arrangement of materials is commonly established by a combination of conductive and resistive yarns. For pressure sensors or matrices, this can be accomplished by stacking layers of respective material to detect pressure at certain areas where these layers are pressed together. For strain sensors, however, these materials are usually knitted directly into a surrounding substrate structure, so the interface effect applies at the intermeshing points of those loops when the fabric is strained. So the current flows along the yarn, and compression of loop head and feet varies the resistance. Note that not only strain but also surface pressure on these points affects the contact between head and feet, so any kind of stress is reflected in the resistance readings and cannot be discerned without external information. You don't know was the fabric pressed or strained. Furthermore, having to integrate those multiple materials into a knit can be limiting in terms of design choices. Visual aesthetics may not be so relevant in some use cases, but the issue goes beyond that. The choice of knitting structure affects not only visual and haptic, but also mechanical properties such as stability, elasticity, wear-out effects, or potential anisotropic strain behavior that you would like the fabric to show. So summarizing, we can state that there is usually a compromise between those three aspects. Latitude in fabrication and sensor integration is usually limited by the required materials. Aesthetic properties are potentially affected, and interaction capabilities are minor, since strain and pressure both actuate the sensor but cannot be discerned. In our work, we address these three issues by knitting a copper wire with polymer coating, which combines both conductive and resistive materials into one strand. Our sensor cells can therefore be established by a single intersection of those coated wires, which can be accomplished by a single stitch. The first prototype of this type of wire was introduced in 2018 by Palazzo and others, who demonstrated feasibility for sewing and weaving, and we also showed the first and rather basic knitted version at SIGCHI 2020. Building on top of those works, we are now able to knit pairs of loops to establish minimal sensor cells at the loop's intermeshing points. Those sensor cells are versatile in that they can be combined with a variety of complex knitting patterns, and depending on the pattern, they can be concealed from the surface. Furthermore, the variation of stitches enables beneficial opportunities for sensing. Addressing the 3 limitations I listed earlier, I will now go into 3 major aspects that we cover in our paper: fabrication, concealment, and sensing. First, fabrication. We knit a Litz wire of 8 strands that is viable for the demanding process of machine knitting. Since common yarn provides some elasticity, but the wire does not, the rapid and jerky movements of knitting machine parts can easily cause wire breaks. To mitigate these effects, we found it essential to use a storage feeder that buffers some wire close to the yarn carriers. Furthermore, we insert the wire courses with minimum carrier speed. This also reduces yarn breaks caused by the sharp edges of knitting needles. We include details and best practices in our paper because fabrication can be challenging without those. For demonstration of successful integration into a plane structure, we show a knitted glove with sensors integrated into the fingers to track joint movements. Second, concealment. We created a line of 3 double-faced knits that demonstrate the design latitude. We integrated 4 sensors across the fabric swatches and sampled them using the ADCs of an ESP board via simple voltage dividers. For side-by-side sensors, we shared the ground electrode to save complexity since it required 3 instead of otherwise 4 courses of wire. We include designs using 1, 2, and 3 yarns. The sensors and traces are visible on the back sides of the fabrics, but are completely unrecognizable on the front sides. The resulting interactive swatches are highly responsive to strain and pressure. Resistance values drop by about 90% in this sample here, so the relative ranges are quite favorable. Note that absolute values are subject to the polymer specification, so ranges can be adjusted by modifying the wire coding. You can find a detailed description of the basic knitting structures as well as respective sensor integration methods in the paper. Third and finally, sensing. Since we are dealing with minimal-sized sensors that only require a pair of loops, we can adjust the local loop mesh geometry without noticeably affecting the surrounding structure. In flatbed knitting, there are several types of stitches. Knit and purl are basically equivalent in this context, but furthermore we can program miss and tuck stitches. And for machines with multiple needle beds, such as V-bed machines, there is also the possibility of loop transfer between beds, which opens up a vast range of meshing options. Due to these diverse physical compositions, we expected different characteristics with respect to actuation modality, since the yarn interaction, meaning the contact and the movement, highly depends on the structure's meshing. We created a number of swatches that implement diverse sensor types and evaluated them with a controlled testing setup. We applied vertical and horizontal strain as well as pressure and analyzed the sensor responses. From the results, we found that yes, the characteristics do vary significantly in between sensor cell variations. The 3 columns here show different actuation types: vertical strain, horizontal strain, and pressure, while different colors in each row represent sensor variations of a subset. I will not go into detail here, but you can already tell visually that the plots are largely different. Now, what can you do with that? You can, for example, choose the sensors that respond best to what you want to measure, and at the same time is indifferent to other actuations to avoid false positives. Or you could even try to infer what actuation you're measuring by selectively combining sensors with certain characteristics. In the simplified case here, imagine we've got 2 sensors A and B. While A responds to vertical but not to horizontal strain, B responds to both. Now when you measure actuation on B but not on A, you can easily tell that we're dealing with horizontal strain. When we measure actuation on both, it would be vertical. We can calculate respective metrics by combining the signals of the sensors A and B. In this case, multiplication and subtraction would suffice. In practice, the response to certain actuation is hardly ever 0, but can be close to 0, which is reasonable for a basic demonstration. Now let's also take pressure into account. Here we have a third sensor C, and we assume we've chosen sensors A and B like in the example before. And furthermore, they both do not respond to pressure while C does. Applying the same principle, we can now by mutual exclusion also tell when we're measuring pressure. To save space and topological complexity, we were furthermore successful in merging 2 of those 3 sensors into a combined cell. In our supplementary material, you can find details of how we implemented the data processing pipeline to infer our actuation modes from the raw sensor signals. We created an exemplary sensor swatch and implemented those methods by a prototypical combination of the sensor's live signals. Here we demonstrate that we are able to discern strain direction using 2 sensors, and on top of that, we are also able to detect pressure using a 3rd sensor. We also demonstrate how you can operate a slingshot with those swatches by discerning between horizontal and vertical strain, or how you can make music by mapping pressure to key velocity and strain to pitch bend. So summarizing, the 5 main contributions of our papers are: a novel minimum scaled knitted 4th sensor cell that only consists of a single pair of loops and can be knitted ready-made, meaning it requires no manual finishing steps, such as stacking and sewing of multiple fabrics. We demonstrate how to conceal these sensors on 3 exemplary fabrics. We investigate the effects of different stitch types and resulting loop meshing with respect to the sensor's characteristics. We show how this can be utilized to expand the textile's input capabilities and infer actuation modalities. And finally, we show some examples of use case scenarios. Okay, thanks very much, and I hope you check out our paper.